Okay, the next important thing about understanding our Lewis dot structures is the polarity of something. So that comes back into the electronegativity that we talked about last chapter. The pull the atom has for an electron. It is a periodic trend, and we talked about that. That as the radius increases, the number of electron shells increases. So the nucleus of an atom has less pull. So as we go down, there's going to be less pull for those electrons. So again, a review from last chapter. As we go across, atoms get smaller, so electronegativity increases. Remember, fluorine has the highest electronegativity of anything. As we move down or away from fluorine, it's going to decrease because, again, those nuclei are going to have less pull for the electrons because they're further away. So what makes something polar? A polar covalent bond is when there's a partial separation of charge, meaning part of it's going to be positive, part of it's going to be negative. So the atom pulls the electrons closer to itself, and that one has a partial negative charge. The atom that the electrons are farther away from has a partial positive charge. And so we're not really totally neutral anymore. So this would be an example where we have two atoms. They're sharing these electrons exactly in the center. Their electronegativities are both 3.0, so they're pulling evenly on those electrons, and this would be nonpolar, okay, because they share equal. Here's another example. We have carbon in the center. We have hydrogen on each side. The electronegativity between carbon and hydrogen is not exactly the same. So carbon is going to pull a little bit more, but the difference really isn't enough to make it a polar bond because the difference is 0.4. Okay, so if we would take the difference between 2.5 and 2.1, the difference is 0.4. That still is considered a nonpolar bond because the difference is not big enough. Here would be an example of a little bit bigger difference. Here we have carbon and hydrogen. Again, we talked about that. That would be nonpolar, so there's really not much of a charge here. But we have a difference between carbon and oxygen here being 1.0. And that's a pretty significant difference in electronegativities. Okay. So what happens is we get a polar bond on that end right here. And so you can see these electrons are much closer to oxygen, so it gets a partial negative charge. That's how we represent it. Carbon has a partial positive charge. Another way you might see this written is with a dipole arrow. The positive part here by the carbon, the negative end is the point end, and so that would be another way that we can represent that this end of the bond is polar because of the difference in electronegativities between carbon and oxygen. So how do we show those partial charges? Again, I wrote those in on the last one, but you can see here partial positive, partial negative, or this dipole where this is the positive end because it looks like a plus, and the pointed end is going to be the negative. Either way is perfectly fine to show a polar bond. Ionic bonds, again, we don't share. But we could see that the electronegativities are going to be very different between a metal and a nonmetal, so those differences are pretty great. So how do we determine our bond type? We can look at electronegativities. We've got a table in our book. You can look them up. Sometimes you're just given them on a worksheet that you're doing. If the difference is 0.4 or less, it's always going to be nonpolar. If the distance is greater than 0.4 but less than 1.4, then it's going to be polar covalent. And if it's greater than 1.4, it's typically ionic. Now again, there are exceptions to this rule. You have to be really careful and remember that an ionic bond is going to be a metal plus a nonmetal. So you also have to look at that. That if it's greater than 1.4 and it's not a metal and a nonmetal, it's going to be polar covalent. So if it's two nonmetals, it has to be covalent still. So you still need to, when you get close to these differences, you still have to look and see what the bond is made up of. Okay, so if we have carbon and hydrogen here, we've got oxygen and chlorine, and we've got fluorine and fluorine. So I'm just going to scroll right down here. We've got 2.5 minus 2.1. Difference is 0.4, so that's nonpolar. Here we've got 3.5 for oxygen and 3.0 for chlorine. So 0.5, so this is going to be polar. The positive end is here. It's showing it. It should be arrow this direction. Then, oh no, I'm sorry, I did that backwards. It's correct. They just put the line in the wrong spot. So the line should be down here. Okay. Fluorine, they're both the same electronegativity, so this is going to be nonpolar because there's zero difference. And then here, the difference is 2.5 and 3.0, so the difference is 0.5, so this is going to be polar also. So mathematically, that's how you figure out the polarity of an atom. Now, if we're looking at shapes, polar versus nonpolar is a little bit different. If a polar bond can cancel out another, it's going to be nonpolar all the way around. So if we look here, this bond is the same as this bond, is the same as this bond, and it's the same all the way around the central atom. So even though this bond could be polar and this bond could be polar, if they're the same all the way around the atom, overall this atom is going to be nonpolar. Here a little bit different. We can see we have free electrons. These always have more pull. So here we're going to have the more negative end being this direction, or we could write a partial negative charge here and a partial positive charge here. So this is going to be a polar molecule because of those free electrons. Okay. Here's a couple other examples that you can see. Again, in 3 dimensions, we can see water here has 2 free pairs of electrons. So it's going to be more negative as we go this direction. So this is going to be a polar molecule with the positive part here and the negative part up here with oxygen. These do not cancel out because they're free electrons. Here is drawn incorrectly because these are going to push the bonds down, so you cannot draw water in this way. This is not correct. You've got to have those free pair electrons at the top so you can show that repulsion and that it is a polar molecule. So make sure you're doing that with your water. Okay, so we have NH3. Nitrogen has 5. Each hydrogen has 1. So this is how we draw our nitrogen. So here, polar bonds, because of the difference, we also have free electrons here. So our overall, we're going to have more negative in this direction for all 3 bonds. And so this is going to be a polar molecule. Okay, electronegativity differences you can see here are 0.9. Trigonal pyramidal shape on that one. You will see that a lot of the shapes, let me go back up here, that if you ever see trigonal pyramidal shape, there's always a free pair of electrons here. So that shape is almost always 100% going to be a polar bond. Bent is the same way. If you've got those free electrons up here at the top in water, okay, if you see those free electrons, always going to be a polar molecule because of those free electrons.